All right, welcome back. Last time we left off with integration techniques. I'm going to start there. Our next technique is called integration by parts. So let me build it really quick. This is it's a little hard to read. Let's go a little bit thicker. Integration by parts. So the idea here is based on product rule. So to start off, I want to know what would happen if I derived u times v.
U times v prime plus v times u prime.
Okay. uv prime plus u prime v. So what we're going to do with is we're going to try to undo product rule with integration. So I'm going to integrate both sides. So now I have the integral of the derivative of uv should be equal to the integral of uv prime plus the integral of u prime v. If I integrate that whole right side, you can split up the integrals at any plus sign because integration is just addition. If I integrate a derivative, then these will cancel. So I'm left with this. uv is equal to the integral of uv prime plus the integral of u prime v. So if I solve our new equation for the integral of uv prime, I'll end up with this. uv minus the integral of u prime v is equal to the integral of uv prime, which is our formula for integration by parts. Now the cool thing about this formula and the reason why it's so useful is because if you notice, we never actually had to integrate whatever we pick for u. We only derive what we picked for u in this formula, and we integrate whatever we pick for v prime. So if we have some part of our function that we cannot integrate normally, for instance, natural log, we can integrate it using this formula because we won't have to integrate that part. Okay, here it is again. So we started with product rule and ended up integrating both sides in order to get our equation, which is our formula for integration by parts. So when we're integrating by parts, we need to pick one part of our integral to be the part that we will derive, that's our u, and one part of our integral to be the part that we will integrate, our v prime. When you're picking your u, there's an order that I like to use as sort of a priority system to decide what should be u. So these are based off of whether or not we can integrate these functions directly and whether or not if I derive these functions, I'll end up getting a constant eventually. So the acronym is ILATE. If you have an inverse trig function, that should be your top priority for setting that equal to u and deriving it. And that's because we can't integrate our inverse trig functions yet. Same thing for logarithms. We can get a logarithm formula. We will get a formula for the integral of natural log of x using integration by parts, but we can't integrate it directly without this method. So that should be our next priority for u. Algebraic functions, those are polynomials. If you've got any kind of algebraic function, when you keep deriving it, it'll eventually become a constant and go away, which is what we want. Any trigonometric functions don't go away, and exponential functions won't go away, no matter how many times we derive them. Okay, so let me throw up an example really quick. So here's our example. I've got The integral of the natural log of x in terms of x. The integral of ln x dx. We can't integrate our natural log of x directly. So I'm going to set this part equal to u. And that means my dx will end up being v prime for our formula. So for our formula, I need u and the derivative of u. So that's ln x, and my derivative of ln x is 1 over x. I also need our v prime, which is dx, and our integral of v prime, which would be x in terms of x. Okay, then I can substitute into our integration by parts formula here. So I could say the integral of uv prime, that's ln x dx, should be equal to u, ln x, times v, x, minus the integral of u prime, 1 over x, times v, x. Okay, for this last integral, 1 over x and x can cancel. So that leaves me with the integral of 1, which is x. So my final answer, if I integrate a natural log of x in terms of x, I should get x ln x minus x plus c. Any questions on what we did here?
No.
Okay. I'm going to go through a couple of these examples on our note sheet. So if you jump up to number 29 on our new note sheet, I've got a couple we can work out together. So for this first one on number 29, which part do you think you would derive and which part do you think you would integrate?
Derive the x um and integrate e to the negative x.
Perfect. So I'm going to derive the x because if I derive the x, eventually that part will go away. So that means in my second integral, we'll only have one part instead of two. And we should be able to integrate directly. So for us, that means u is equal to x. And u prime then is equal to dx. My v prime should be equal to e to the negative x. And if I integrate v prime, what will I get?
Negative e to the negative x.
Perfect. Okay, so I'm going to substitute in our formula. Let me write our formula up here again. If you want to integrate uv prime, you'll end up getting uv minus the integral of u prime v. So I've got uv. This is negative x e to the negative x minus the integral of u prime v. So that's dx times negative e to the negative x. Okay, now we only have one part here that we need to deal with for this integral. I can pull out this negative 1 to cancel it, so that'll give me negative x e to the negative x plus the integral of e to the negative x. And then we've already integrated e to the negative x dx when you integrated v prime. So my final answer will be this, negative x e to the negative x plus, if I integrate e to the negative x, I get negative e to the negative x. This will become a minus actually, negative e to the negative x plus c. Okay, I'm going to rewrite these. Anytime we have a negative exponent, I can move that to the bottom of a fraction. So this is negative x over e to the x minus 1 over e to the x plus c. Any questions on what we did?
Can you please scroll down a little bit?
Okay. Can you see the whole thing?
Yes.
Okay. Any questions on what we did?
No.
Okay. Let's try the next one together then. So for number 30, which part do you think we will derive, and which part do you think we will integrate?
Derive the x squared and then integrate the x 2 to x.
Perfect. So I'm going to derive the x squared. That'll give me 2x, and we will integrate 2x dx. What do you think will happen if I integrate 2 raised to the x power?
Ln to the um I'm not sure.
Okay. So we know that if we derive a real number raised to the x power, we'll get a to the x ln a. So when I derived, I multiplied by the natural log of a. So when I integrate, what do you think will happen?
Oh, it's 2 to the x divided by ln 2.
Perfect. So we integrate, we'll do the opposite. So I should divide by ln 2. So this is 2 to the x over ln 2. Alright, so now I'm going to plug into my formula. Let me write our formula one more time. So this is, if you integrate uv prime, you'll get uv minus the integral of u prime v. So I have uv, this is x squared 2 to the x over ln 2, minus our integral of u prime v, 2x 2 to the x over ln 2. So I'm going to pull out our constant. So our constant is 2 over ln 2. And that will leave us with a new form we need to deal with. So this is x squared 2 to the x over ln 2 minus 2 over ln 2 times the integral of x times 2 to the x. Okay, for our new integral, we still have 2 parts. Which part do you think we need to derive?
The 2x.
Okay, if I derive the 2x, 2x is an exponential. So I'll end up with 2 raised to the x power in my answer, and then I'd have to integrate the x and then get back to an x squared. So if I derive the 2 to the x, that'll get us into an infinite loop, unfortunately. So what should my u be?
So derive the 2 to the x 2 to the x power.
Okay, if I derive 2 to the x power, we'll be stuck in an infinite loop. Because if you derive 2 to the x, you get 2 to the x times ln x, right? So that will not help us get rid of a power. It won't help us get rid of a part. So I'm actually going to keep deriving this polynomial part. If I do, what's going to happen? I have to derive the x part, because if I derive the x part, that will eventually go away. It will become a constant. If I try to derive this 2 to the x over here, I'm still going to have a 2 to the x in my answer, and then I'll have to integrate the x will become x squared, so I'll be stuck in an infinite loop. What happens if I derive x?
Dx, 1 dx.
1 dx, okay. So that means my v prime must be 2 raised to the x power, which we've already integrated once up here. So that means my new v is also 2 to the x over ln 2. Alright, so I'm going to substitute. So this will be x squared times 2 to the x over ln 2 minus 2 over ln 2 times all of uv. So that's x times 2 to the x over ln 2 minus the integral of u prime v, or 2 raised to the x power over ln 2 dx. Okay, for our last integral that I have here, I can pull out my constant, 1 over ln 2. So that'll give me this, x squared times 2 to the x over ln 2 minus, I'm going to go ahead and distribute this while we're here. So this will be 2x, 2 raised to the x power over ln 2 squared. Plus, because I have a negative times a negative, 2 over ln 2 squared times the integral of 2 to the x dx. Okay, I only have one part left, and we've already integrated 2 to the x 2 times now. If I integrate 2 to the x, we should get 2 to the x over ln 2. So I'm going to make that substitution here, and we'll be done. So x squared 2 to the x over ln 2 minus 2x to the x over ln 2 squared plus 2 times 2 to the x over ln 2 squared times ln 2 is ln 2 cubed plus c. Okay, I'm going to zoom out so we can see the whole thing. Any questions on what we did?
No.
Okay. So before I move on, I'm going to give us a shortcut. Now this shortcut only works if we have parts that end up canceling like these two did. So if you can cancel one part, then we'll be able to use this shortcut. So this one is on your integration by parts worksheet if you want to follow along from WeChat. So before I give this, I need to talk briefly about different integral notation. So far, we've been able to talk about derivatives using both of these notations, where this would be n is how many times that I have derived a function. So I could write this is the fourth derivative of x, or I could write this as the fourth derivative of y in terms of x. But we don't have a good way for talking about what happens if I take the second integral of a function. And if I'm going to create a shortcut for integration by parts, we need to talk about the nth integral of a function as well. So different integral notation, to simplify things, looks like this. So we just write d, which is how many times that we have derived. Some number that tells you how many times we've derived of our function f. Now if q is negative, so if I put a -1 here, then instead of deriving, we would have integrated our function that many times. So this d to the -1 f says that I have integrated my function of f once. If I change this to d to the -4 of f, that means I would have integrated my function 4 times. If I make this a +4 instead, then I have derived my function 4 times. Okay, here's a couple examples. d3f is your third derivative of f in terms of x. d-2f is your second integral of f in terms of x. And we could replace those with any number you want. Any questions on the new notation?
What is the -2? The d -2 means.
So it means that instead of deriving, because this is negative, I will integrate. And the 2 tells us we have integrated twice. So instead of just one integral of f of x, I'm going to take whatever the integral of f of x is and integrate again.
Oh, okay.
Okay. So if you have a negative number here, we've integrated this many times. If we have a positive number, we have derived this many times. If you see a 0, that means we have not derived or integrated. So we just have our function.
Okay.
Okay. So with that, I'm going to rewrite our formula for integration by parts using our new different integral notation. So our integral by parts formula was this. The integral of uv prime is equal to uv minus the integral of u prime v. So in different integral notation, that means I would have had to integrate, so that's d to the negative 1 of v prime to get v. And the same thing here for our second integral. I would have integrated v prime once to get v in my original formula. Okay, any questions so far?
No.
No. Okay. So if I integrate this part, I'll have another integration by parts. So our new u is u prime. So if I integrate u v prime, I should get uv minus the integral of u prime v. So I have, if I integrate u prime times my first derivative of v. My first derivative of v will be v prime, so that means all my v's will be the, my first integral of v prime. When I integrate that, I will get my second integral of v prime. So I'll have u prime, that was my first part, here, times my second integral of v prime, here, minus my integral of my derivative of my first part, so that's u prime prime, times my integral of my second part. That's my second integral of v prime. Okay. If I distribute our subtraction sign, then I can start to see a pattern. Right now, when I've integrated, I had u times my first integral of v prime, minus u prime times my second integral of v prime, plus if I integrate this one and break it apart again, I get the second derivative of u times my third integral of v prime. And that pattern actually continues forever. So if you integrate uv prime, you'll end up with u times the first integral minus u prime times the second integral plus the second derivative times the third integral minus the third derivative times the fourth integral plus the fourth derivative times the fifth integral. It's going to keep going on and on and on.
And so this is basically like plugging in this function, this equation to itself again and again, right?
Right. So I'm continuing to do integration by parts again and again and again and again. And if you do in a general form, you start to see a pattern. That pattern is I'm always taking my first part, and for my next term I'm deriving it one more time. And I'm always taking my second part. For my next term I will integrate one more time. My sign also alternates, so I start with positive and then negative, positive and then negative, positive and then negative. Okay, if I wanted to write this as a sequence, my infinite sequence would look something like this. Okay, I also alternate in sign. So my first term will be positive, second term will be negative, third term will be positive, fourth term will be negative. Okay, so with that pattern, we can create a shortcut, which we'll call tabular integration, which will look like this. I'm going to start off by creating a table of values for what we want to integrate by parts. So here I have the integral of x squared sine x. So I'm going to put everything that I'm going to derive on the left side and everything that I'm going to integrate on the right side. So my first part, this is my u, which is x squared, and my second part is my v prime, is the sine of x. Then I'm just going to work my way down and keep deriving the parts that I will derive and integrating the parts that I will integrate. So if I derive x squared, I get 2x. If I derive 2x, I get 2. If I derive 2, I get 0. If I integrate the sine, I get negative cosine. If I integrate negative cosine, I get negative sine. Then cosine, then sine. Okay, any questions on what we've done so far?
No.
Okay. So once again, take your part that you would have for u and derive it until you come to 0. Take your part that you would have for v prime and integrate it. Okay, so once we've got our table, then I'm going to create an arrow from each u value to the next integral of v prime. So this connects my first u with the integral of v prime. So this is u times v is my first term. Okay, my second term will be based on my derivative, u prime times the second integral. So that's first derivative and the second integral will go together. The second derivative and the third integral will go together. The fourth derivative and the fifth integral will go together. Okay, so I'm just creating diagonal arrows going from the part we derived to the next part that we would integrate. Okay, and these also alternate in sign. So I'm going to take our table and we're going to add signs to it. So that one's cut off a little bit, so I'm going to add my signs here. Plus, minus, plus, minus. Any questions on what we've done so far?
No.
All right. Okay. So then my integral for this should be equal to what happens if I put this all together. So when I multiply these together, I'll get this. Our original problem was the integral of x squared times the sine of x should be equal to my first two terms, x squared times the negative cosine of x, and it's positive. So that's positive x squared times negative cosine x is negative x squared cosine x. Minus 2x times negative sine x. A negative times a negative is a positive. So that's plus 2x sine x plus 2 times cosine x minus 0 times sine x. Now every term after this is going to be 0 because if we multiply anything by 0 we get 0. So now I'm at the end. So I can add my plus c and we're done. Okay, I'm going to go back and we'll solve this using our long method just to make sure that it matches. And then we'll try this shortcut with one of the ones we already solved. So let me grab a blank sheet here. Okay, so I want to integrate x squared times the sine of x in terms of x. If I was going to use the old method, which part of this would be my u, the part I want to derive, and which part would be the v prime, the part I want to integrate?
U equals x squared and sine of x is sine x is v prime.
Okay. If I integrate sine, I get negative cosine. So I have, write my formula again. The integral of uv prime is equal to uv minus the integral of u prime v. So I have uv prime x squared sine x. Oops. Just made a mistake. I'm writing my original problem. Okay, never mind. Integrating x squared sine x should be equal to uv. So that's negative x squared cosine x minus the integral of u prime v minus 2x times negative cosine x. Okay, I'm going to pull out all of my constants. So this is negative x squared cosine x. I've got a negative times a negative should give me a positive, and I'm going to pull out the 2. The integral of x cosine x. Okay, I've got another integration by parts. For our new integration by parts here, the integral of x cosine x, which part would you derive?
Derive the x and cosine is d prime.
Perfect. So if I derive x, I get dx. If I integrate the cosine of x, I get the sine of x. That leaves me with negative x squared cosine x plus 2 times all of uv minus the integral of u prime v sine x dx. Okay, and then if I integrate sine, I should get negative cosine. So that gives me negative x squared cosine x plus 2 times the integral of x sine x minus negative cosine. So that's plus cosine x plus c. And then I'm going to distribute the 2. So I'll have negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. Okay, let's see if we match. Okay,
We don't have to times 2 to the c, right?
If you do, 2 times a constant is a constant, so 2 times c is c.
Oh, okay.
Okay, and we do match, so negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. Okay, so I'm going to do that same problem one more time from scratch using our shortcut method just to show you how much faster this is. Create a new one here, and we'll close out the other one. So if I wanted to integrate x squared sine x in terms of x, I'm going to make a table of everything that we want to derive and everything that I want to integrate. Okay, I'm going to derive x squared, and I will integrate the sine of x. If I derive x squared, I get 2x. If I derive again, I get 2. If I derive again, I get 0. If I integrate sine, I'll get negative cosine. If I integrate negative cosine, I get negative sine. And if I integrate negative sine, I get positive cosine. Okay, then I'm going to draw my arrows. So I've got diagonal arrows showing me which parts will go together. And then alternate my signs. So this is positive, negative, positive, negative. Okay, putting it all together, my final answer will be negative x squared cosine x minus negative 2x sine x, so that's plus 2x sine x plus 2 cosine x plus c. Okay, that was way faster than doing 2 integration by parts. Any questions on the new method?
No.
Okay, let's go back and we'll do our new method with some of our ones that we've already solved. So I'm going to redo this one, number 29. Okay, while I'm erasing here, if I'm going to use the new method, what's the first thing that I have to do?
Create a table of u and u v prime.
Okay, I'm going to create a table of u and v prime. What is my u and what is my v prime?
It's x and x e to the negative x.
X and e to the negative x. Okay, so right now, my u is everything I need to derive, and my v prime is everything I need to integrate. So what do I do next?
Um, Derive. So
Mm,
it's dx.
dx. Um, okay, and then what happens if I integrate e to the negative x?
Negative e to the negative x.
Okay, what happens if I derive dx?
Um, is it going to be 0 or is it going to be the second derivative?
So it'll actually be 0. My derivative of x is 1. So if I derive 1, that's a constant, I'll end up getting 0. Okay, what happens if
Oh, okay.
I'm going to leave this as 1 for now. Okay, what happens if I integrate negative e to the negative x?
E to the negative x.
Okay, I'm going to do one more step. What happens if I integrate e to the negative x?
Negative e to the negative x.
Okay, what do I do next?
Put the arrows.
Okay,
And then put plus and minus and plus.
alright. So plus, minus, plus. Okay, now what?
So now it's equal to x times um, negative e to the negative x,
Okay,
and then oh wait, it's actually it is negative, and then minus 1 times um, e to the negative x, yeah,
okay.
and then plus um 0 constant.
Plus 0, and then I'll need a constant of integration, so every term
Uh,
after this will still be plus 0, so this will be plus c.
yeah.
Alright, and if I needed to, I could rewrite this like we did last time, so this would be negative x over e to the x minus 1 over e to the x plus c, which is the same answer we got last time, but a lot faster. Okay, so if you make a table and you realize that when you derive you eventually get 0, then it will be way faster to do the table if you've got a lot of integration by parts. Especially once we start getting to something like x to the 6th power. If you do this the old way, you'll have 6 separate integration by part problems to do, and it's really easy to miscarry a negative or make a mistake. Whereas if you make a table, it'll be a lot faster. But if you have a problem where when you're deriving you don't end up with a constant, we'll have to use the old way. So I've got a couple examples coming up. Okay, here's one for number 31. I've got the arctangent of x times dx. Which part do you think is u, and which part do you think is v prime?
Um, U is tangent, arctangent, and the v prime is dx.
Perfect. U is the arctangent, and v prime is dx. Remember, our inverse string functions are always the top priority for what we want to derive, because we can't integrate them directly. Okay. If I tried to do a table for this, I'm going to write d for derive and I for integrate. I would derive the arctangent of x, which would give me 1 over x squared plus 1. And then I'm stuck, because I'm going to keep deriving this forever. and I'll never end up at 0. So that's my clue that I can't use my shortcut method. I have to do this a long way. And hopefully something will cancel after I integrate this v prime. Okay, so if I derive the arctangent, I get 1 over x squared plus 1 times dx. If I integrate dx, what will I get?
X.
X. Okay, so I'm going to plug that into our integration by parts formula. So that gives us this. uv, so x times the arctangent of x minus the integral of u prime v. So that'll be x over x squared plus 1. Okay, so at first glance it looks like I still have 2 parts, but I can actually integrate this directly. If I wanted to integrate this using u substitution, what could I do?
Substitute u for x squared plus 1.
Okay, so that means my u prime would be 2x dx. I don't have a 2 on top, and I need to have a 2 to substitute for u prime. So what can I do?
Times 1/2 to the whole interval.
Perfect. So if I make that substitution, I'll have 1/2 times 2 is 1, so I have not changed anything. Okay, so now I've got u prime that I can substitute for, 2x dx, and u, x squared plus 1. So that means this is really x times the arctangent of x minus 1/2 times the integral of u prime over u. What happens if I integrate u prime over u?
Ln u.
Ln u, perfect. So this is really... I'm going to erase so I have a little bit more space. U prime is 2x dx. Okay, this was x times the arctangent of x minus 1/2 times the integral of u prime over u, which we said was x times the arctangent of x minus 1/2 ln of u, where u is x squared plus 1 plus c. Do you remember from last time why I used absolute value signs here for my natural log?
Because it's undefined for negative numbers.
Perfect. We can't take
But it's actually squared. But it's actually squared inside.
Yes. So no matter what we plug in, that one's going to end up being positive anyways. All right. So we had to use the old method with that one because we didn't end up getting 0 after we derived. So that's going to be true for all of our inverse trig functions actually. So for this arcsine function, we're going to have to do the same thing and use the old method. I'm going to skip arcsine for the sake of time since we have 10 minutes left. We're going to use the same process for this arcsine one. And I'll let you guys try that one on your own. The last thing I want to talk about is recursive integration by parts. So far, we've always been able to cancel one of the parts. But if we look at this one, I've got the integral of e to the x times the sine of x. No matter what you pick to derive, they're never going to go away. If you choose u to be the sine, then when I derive, I'll get cosine, again, negative sine, again, negative cosine, and then again back to sine. So I'll be in an infinite loop if I pick u for sine. And if I pick e to the x, no matter how many times you derive, you're still going to get e to the x. So I'm in an infinite loop no matter what I do. So what I'm going to do is, I'm actually going to use that to my advantage and force myself into an infinite loop. So the key here is whatever you pick for u, it doesn't matter which one you pick. but we have to stay consistent all the way through. So if you choose u to be e to the x, that part has to stay the part that you derive all the way through. Okay, so here's what it looks like. I am integrating e to the x sine x in terms of x. I'm going to say u is equal to e to the x, therefore u prime is equal to e to the x dx. And v prime is equal to the sine of x dx, therefore v is equal to negative cosine of x. Okay, so that means the integral of e to the x sine x dx is equal to uv, negative e to the x cosine x, minus the integral of u prime v, negative e to the x cosine x. Okay, I'm going to pull out my constant. So this will be integral of e to the x sine x dx is equal to negative e to the x cosine x plus the integral of e to the x cosine x. And this is important. Last time I picked e to the x as u, so I'm going to do that same thing again. U needs to be e to the x again. U prime will be e to the x again. My new v prime is cosine. If I integrate cosine, I get sine. Okay. So substituting, this is the integral of e to the x sine x is equal to negative e to the x times the cosine of x plus uv. Actually, don't need parentheses there because I already pulled everything out. So uv e to the x sine x minus the integral of u prime v e to the x sine x. Okay, I'm right back to where I started, right? This integral was the same integral that I had originally. But because I am subtracting, I'm subtracting the same thing that I have on the left side of the equation. I can actually add the integral of e to the x sine x dx to both sides of my equation. Leaving me with 2 times the integral of e to the x sine x is equal to negative e to the x cosine x plus e to the x sine x. Okay, and then all I need to do is divide both sides by 2, and I've got my answer. So the integral of e to the x times the sine of x should be equal to everything that I had originally divided by 2. Negative e to the x cosine x plus e to the x sine x divided by 2. And then plus c for our constant of integration that I would have had at the end of all of these integrals. I'll go ahead and add that to this step too, but any questions on what we did?
No.
Okay, I'm going to zoom out again. So this new idea is we are forcing ourselves into an infinite loop, trying to get the original problem that I had on the left side of the equation, integral of e to the x sine x, as our integral again, but with a negative sign. Because if it has a negative sign, I can add it back to both sides and then divide by a constant to get an answer. Okay, last problem for today is going to be the same idea, but a little bit trickier with our constants. So last problem. I want to integrate 4 to the x times the cosine of 4x. Once again, I've got an exponential function and a trig function, so no matter which one you pick, we'll be stuck in an infinite loop. So we're just going to pick one, and whatever you pick to derive will continue to derive that function So if you pick the exponential, we'll keep deriving the exponentials all the way through. If you pick the trig function, we'll keep deriving the trig functions all the way through. What do you want to derive?
4 to the x.
Okay, so u is 4 raised to the x power. What happens if I derive 4 to the x?
Um, 4 to the x divided by ln 4.
Close. That's actually what happens if I integrate. So if I integrate, I divide by natural log of 4. So if I derive, I should do what? Okay, if you derive a to the x, you get a to the x ln a. So if I derive 4 to the x, I should get 4 to the x times the natural log of 4. When you derive, you multiply by the natural log of your base. So when I integrate, I would divide by the natural log of our base. Last time we were integrating, so we divided. This time we're deriving, so we had to multiply. Okay, then my v prime is the cosine of 4x. So if I integrate the cosine of 4x, what will I get?
Negative sine 4x divided by 4.
Okay, really close. I want to know what I would have to derive in order to get the cosine of 4x. So this will actually end up being a positive sign. Positive sine of 4x divided by 4. Okay. So let's write our problem out. This is the integral of 4 to the x cosine 4x is equal to uv. So that's, I'll write 1/4 times 4 to the x sine 4x minus the integral of u prime v. So that's minus the integral of 1/4 sine 4x times 4x ln 4. I'm going to pull out all of my constants. That's my ln 4 divided by 4. Integral of 4 raised to the x cosine of 4x equals 4 to the x sine 4x over 4 minus ln 4 over 4 times the integral of the sine of 4x times 4 raised to the x power. Okay, I don't have my original function back yet, so I need to do integration by parts one more time. Last time we derived the 4 to the x, so I have to derive the 4 to the x again. So my new u is 4 to the x again, and my u prime again is 4 to the x ln 4. My v prime is the sine of 4x. What will happen if I integrate the sine of 4x?
Negative cosine 4x divided by 4.
Perfect. Negative cosine 4x divided by 4. Okay, so I'm going to plug all that in. Let's make this a little bit bigger. Okay, I have the integral of 4 raised to the x cosine 4x is equal to 4 raised to the x sine of 4x over 4 minus ln 4 over 4 times all of uv negative 4 raised to the x power cosine 4x over 4 minus the integral of u prime v. So I have 4 to the x ln 4 cosine 4x, and it's negative over 4. Okay. Any questions on what we've done so far?
No.
Okay. I'm going to go ahead and distribute everything that I've got in here, and we'll pull out our constants out of this integral. So that'll leave us with this integral of 4 to the x cosine of 4x is equal to 4 to the x sine 4x over 4. I've got a negative times a negative should give me a positive, so this is plus 4 to the x cosine 4x ln 4 over 16. A negative times a negative is a positive, and I've got, negative times a negative again. So I've got negative times a negative times a negative is a negative. I can pull out the ln 4 over 4, so that'll give me ln 4 squared over 16. Times the integral of 4 to the x cosine 4x. Okay. So right now, these two terms are really the same. I'm subtracting a constant times my integral of the original function, so I can actually add back ln 4 squared over 16 of that original function to both sides. Okay, so if I do that, this will be this plus ln 4 squared over 16 times my integral of 4x cosine 4x to both sides. Okay. So to give myself a common denominator, this was 1 times what I had originally, which is the same as 16 over 16. So if I add these together, I should get 16 plus ln 4 squared over 16. Times our original function. Should be equal to everything that I had on the other side. 4 to the x sine 4x over 4 plus 4 to the x cosine 4x ln 4 over 16. Plus c, because we've gotten rid of all of our integrals on that side. That was the hard part. Any questions on what I did there?
No.
Okay. So the last part is I'm going to multiply both sides by 16 and divide both sides by 16 plus ln 4 squared. So that'll give us this. The integral of 4 to the x cosine 4x should be equal to, I'm going to write this out first, 16 over 16 plus ln 4 squared times all of this. I'm going to go ahead and give myself a common denominator here. So if I multiply this term by 4, I'll end up with this. 4 times 4 raised to the x power times the sine of 4x. over 16 plus my other term is also over 16, so I can combine them. 4 to the x ln 4 cosine 4x. Okay, plus c. So my 16s on top and bottom will cancel. And that leaves me with my final answer. The integral of 4 to the x cosine of 4x should be equal to 4 times 4 raised to the x power times the sine of 4x plus 4 raised to the x power times the natural log of 4 times the cosine of 4x, all divided by 16 plus the natural log of 4 squared, plus c. Again, that plus c, I did actually multiply this constant by that plus c, but a constant times any other constant is still a constant.
Okay.
Alright, I'm going to zoom out so we can see the whole thing.
So on the test, we don't have to actually simplify it, right?
No. So if you're on your AP exam, you only have to simplify on the multiple choice. As long as you have your answer correct, you're okay for the free response.
Okay.
Alright, we are 10 minutes over time, but we had some technical difficulties in there, so we're actually on time for the recording. The next 2 class periods, I'm going to try to focus a little bit more on getting more AP free response questions into the video, so we'll have less teaching time and more just jumping in and doing some practice with integration and related rates. We've got a couple topics that people have sent in to me that they wanted a video for, including optimization, so we'll hit that on Friday. Thanks a lot for coming, and I'll see you next time.
Oh, thank you. Can I ask you a question real quick?
Yeah, go for it.
Is the AP exam going to be on paper or is it online?
It's all on paper.
Oh, okay.